Dear students, in this lecture, we are going to see what is meant by standing waves and what is the formula to find the standing wave ratio. We all know that if the load on a transmission line, that is if the transmission line is terminated by an antenna, then the signal that is transmitted from the source to the load will be converted into an electromagnetic energy and it will be radiated into space. That is, if the load is an antenna, the signal will be radiated into space. The second case is if the load is equal to the characteristic impedance of a line. If the load is equal to the characteristic impedance of a transmission line, then the signal that is transmitted from the source will be absorbed by the load and it is dissipated as heat. This is the second case. The third case is if the load at the end of the transmission line is either an open circuit or a short circuit. If the load is either an open circuit or a short circuit, or it has an impedance which is not equal to the characteristic impedance. That is, whenever ZL is not equal to Z0. Now, in this case, the signal will not be fully absorbed by the load. It is not absorbed completely by the load. These are the three types of load that we can connect at the end of the transmission line. One is, if it is an antenna, the signal will be radiated as electromagnetic energy into space. If the load is terminated with an impedance equal to the characteristic impedance, then the signal will be completely absorbed and it will be dissipated as heat. Absorbed and dissipated as heat. The third case is whenever the line is an open circuit or a short circuit, or if the impedance, that is a load impedance, is not equal to Z0, then in that case, the signal will not be completely absorbed by the load. And this also is a known concept to us. That is, a transmission line is said to be a matched transmission line if the line is terminated with an impedance, with a load impedance, which is equal to the characteristic impedance. So if the impedance at the load is equal to the characteristic impedance of the transmission line, then we can name that the transmission line is a matched transmission line. And this is the power that is sent down the line toward the load, from the source to the load. If we are transmitting the signal from the source towards the load, we name it as incident power. It is called incident power. Similarly, the power that is not absorbed by the load, the power that is not absorbed by the load is called the reflected power. So this is the power which will be reflected back from the load towards the source. If the power is not absorbed, that is, if this condition is not satisfied, if ZL is not equal to Z0, complete power will not be absorbed by the source, and a part of that is power will not be absorbed by the load. Part of power will be reflected back to the source, and this we are naming it as reflected power. This is called reflected power. An example of a transmission line is given here. This is the source. Here we have a transmission line. This is called source impedance, or you can name it as generator impedance. The impedance is now 50 ohms. At the other end, we are going to have a load. The load is mentioned here as an antenna. The load impedance is also equal to the characteristic impedance of the transmission line, which is equal to 50 ohms. So in this example, which is drawn here, the transmission line is having the load impedance equal to that of the characteristic impedance. So we can say that this is a matched transmission line and the power will be completely absorbed by the load. There won't be any reflected power. So reflected power is absent in such a matched transmission line. This is what we can observe. Now, if the line is not terminated properly, whenever the line is not terminated properly, a part of energy is reflected and it will move back up the line towards the generator. Now, this reflected voltage adds to the forward voltage because initially the signal will be moving in this direction, that is from source to load. Now, since ZL is not equal to Z0, part of power will also be reflected back from the load to the source. So now the signal will also be traveling from the load towards the source. This way also it is possible. Now this reflected voltage will add with the forward voltage and it forms a composite voltage which is distributed along the transmission line, right? And this pattern of composite voltage as well as its related current wave, we are naming it as standing wave. So signal will be moving in either direction. One is moving from source to load. The other one, it will be moving from load towards source also in this direction. This signal is moving in this direction. Okay. And this wave is called as a standing wave, right? And these standing waves are not desirable characteristics of a transmission line. We have to make sure that in a transmission line, the standing waves are reduced. Standing wave should be very less. And this picture, it depicts the standing waves. See here, this blue line. This blue line represents the signal that is flowing from the source end towards the load end. So from here to here, the signal is traveling and this wave, we are naming it as incident wave. Now, if this load impedance is not equal to the characteristic impedance, reflection will take place and this reflected wave will be moving from load towards source, and this is represented here as in dotted green line. This represents the reflected wave. Now, in the first picture, we can see that the incident and the reflected wave are completely out of phase. They are completely out of phase with each other. Incident and the reflected waves are completely out of phase with each other. So here, the resultant at this red line represents the standing wave, and here it is 0. It's constant. Okay, and this point of minimum value of the standing wave, we name it as nodes. But in some cases, the incident and the reflected waves will not be completely out of phase with each other. And in cases where the incident and the reflected waves are in phase. So this second diagram shows the incident and the reflected waves are in phase with each other. See here, this blue line represents the incident wave, green line represents the reflected wave. So now both are in phase. Now, since both are in phase with each other, the resultant standing wave will have an amplitude which is higher than that of the incident and the reflected wave, because here the amplitudes of both the incident and the reflected wave gets added together to form the standing wave. So now this point of maximum or peak voltage of standing wave, we name it as antinode. So in a standing wave, the minimum points or minimum value is referred to as nodes and the maximum value is referred to as the antinode. Okay. Now coming to the formula to find the standing wave ratio, it is determined by the ratio of maximum current to the minimum current, or you can say with respect to voltage, it is the ratio of maximum voltage to the minimum voltage along the transmission line. So the formula or the expression for transmission line is I max by I minimum, or you can say V max by V minimum. This standing wave ratio, in short, it will be represented as SWR, and this SWR can also be expressed in terms of, that is reflection coefficient gamma. So reflection coefficient is given by V max minus V minimum by V max plus V minimum, which will give us a value of SWR minus 1 by SWR plus 1. SWR in terms of reflection coefficient is 1 plus reflection coefficient divided by 1 minus reflection coefficient. Thank you.